Hi, and welcome to the Vintage Computer Federation YouTube channel. Your support helps us with creating videos just like this one and restoring vintage computers for all the world to enjoy. So please like, share, and subscribe. Thank you.
Pennywhistle Modem was the result of many things. First of all, there's Stretch, the big defense computer system, 1958, required teletype communication by phone. And so Bell System got to work, came up with the protocols, and came up with the 101 protocol, which was a half duplex, one way at a time. 110 baud, which is what the teletypes ran out. And nobody much used it. But they also did the 103 protocols, which is full duplex. And so the receiving frequencies for at the terminal end, DTE, was 2025 and 2225 hertz. I think the higher frequency is 0, and the lower frequency is 1. Transmitting 1070 and 1270 hertz. Fairly simple. Well, what they did then was, working with Teletype Corporation, they built modems into the bases of teletypes, especially ASR 33s, which we're all familiar with. And those were a computer terminal in the day. 110 baud, 10 characters per second, 11 bits per character. And this will be important. There'll be questions on the test. One start bit, 2 stop bits. And the stop bit can last forever. This is asynchronous data communication, you understand. So that is the marking condition. The 1 state is the natural state of the line. And this dates back from telegraphy, where your normal circuit is closed and your key opens the circuit when you hit it. That way you can tell the difference between a line that is connected properly and one that is accidentally open. So that goes on to teletypes in their current loop configuration work that way. They will pass current normally, and they will interrupt it when the distributor rotates, which is what happens when you press a key. I'm still trying to find my cursor, and it's not responding to this, so okay, too bad. Here you can see some of my notes that we're going to wind up in slides. The early efforts, well, the Carter phone decision in 1968 jump-started third-party modems. And what they would have is a nice varnished wooden box about the size of a shoebox and a little bit bigger. And there would be a lid that lifts up and opens up part of the box, and there would be 2 rubber cups, and you put the handset from the Bell 500 desk set in there, close the lid, and you were in business. 110 baud was the limit. And it didn't care about start and stop bits. Those modems sold for about $350. And how do I know this? Well, I was there. In 1973, you see down the CM requirements. CM stands for community memory. That was the big one for me. That was the first social media system, and I was heavily involved with it. We set it up on a 940 computer in San Francisco, which just happened to be the same computer that Doug Engelbart had run his mother of all demos on. Returned from lease, and through process that we can't repeat, given to our nonprofit on long-term loan, which means don't bring it back. And I had the joy of being the engineer responsible for setting the whole thing up while not knowing how. You should all try this someday. It forms character. It was a time-sharing computer. In fact, the 940 was the first computer built for time-sharing. The Project Genie at Berkeley had managed to force Scientific Data Systems, which was manufacturing the computer, to agree to manufacture a time-sharing system in exchange for the software to do time-sharing on, the multiple access memory and so forth. Scientific Data Systems did not have this in their plans, but they had to do it. They loaned a 9300 to Berkeley, and over the years from 1966 or so to 68, they got the time-sharing running. 57 of 940s were ever built. Half of them were used by the TYM Share company, timeshare, in Cupertino. And our little group, with our amazing hustling, got 3 or 4 used, clapped out teletype ASR 33s given to us for a tax deduction. Now, I showed up there in 1971 to begin with, and had this strange idea of public space on the computer. That is to say, bulletin board system, pretty much open to everybody and not pre-categorized. I didn't know how to do it, but these people had the computer to do it with, and I brought along a few other people, Ephraim Lipkin, Ken Kolstadt, Mark Spikowski, and Judith Milhon, later known as St. Jude. At one point, I remember Ricky Greenblatt, we called him Ricky in those days, Richard Greenblatt from MIT, legendary hacker, visited for a few days. This was at Project One, which was a warehouse community. There's a whole story behind that. I'm not going to go into it now. See my forthcoming book. And he waved his arms and said, let's make an information retrieval system in 24 hours. Well, it didn't really work that way, but it started the ball rolling. And so we developed Resource One Generalized, Resource One's the name of the corporation, Resource One Generalized Information Retrieval System, Rogers, and had that pretty much ready in 1972. Then it was a question of who's going to use it. The corporation had been a spinoff of a renaming of the San Francisco or the Haight-Ashbury switchboard, split into two, as was the fashion in those days. One was the San Francisco switchboard. They took the corporate papers. They wound up as Resource One's corporate papers. So we had this sort of cultural contact with switchboards, which, as some who were not there may not remember, are volunteer information referral agencies. The name is much more formal than they were. These are basically, like the big one was the Haight-Ashbury switchboard, which did a lot of business with connecting or parents finding their kids who had run away. But these were all manual filing systems, such as they were, to the extent that they were filing systems. Usually it was some one person who heard everything happening and kept it in their heads and eventually burned out and left, and they had to start all over again. Well, we thought they could use a computer database system. They weren't thinking that way, unfortunately, as we found out. And they also didn't have any money, so they couldn't rent a teletype for $150 a month, which was the price in those days. So there we were. We had a bulletin board system and nobody to access it. Some of our people, not me included, met with some librarians. There's a county interlibrary service. And they said, well, it looks like you've got a library with no books on the shelf. Why don't you put some books on the shelf and see who comes? And we thought we could do that. So we came up with a few places, talked them into putting a terminal there. Our terminal. We would provide the terminal. They would just give us the use of the space. And the first one we started, I think it was August 8th of 1973, was at Leopold's Records. Originally the Leopold Stokowski Memorial Service Pavilion, which was a student government-owned record store created to drive record prices down, which it did successfully. And we came to the ASUC council and said, here, we got this, we want to put a terminal in there and do this. And they said, hey, it sounds great, go ahead and do it. I like that kind of negotiation. They should all be like that. And so we set up, now I got some pictures, oh God, in here. Sorry about that. You probably have all, maybe you have all, some of you, oh, hello, here's the login screen again. No, wait, sorry for a moment. All right, we get that. Mouse is useless. Hang on. We've got here. Yes, and it says, yes, I'm there, thank you. That's not what I want, and I'm looking for pictures. We want pictures, pretty pictures. Okay, you'll have to use your imagination on this one. You go up you come off Telegraph Avenue, which is the main artery into this campus, floods of students in there every day. You go up 1/2 block on Durant Street. There's a place, 2518. You go in upstairs, up a flight of stairs, down a hallway to get to Leopold's Records. But in the hallway, there's a bulletin board, and it's used by a lot of musicians and so forth. And there is where we put the terminal. Now, the terminal is an ASR 33, tabletop, no stand. And we had to silence it, so I built a cardboard box lined with a urethane foam. And it had two hands. I have a picture of it in here, and I think I said, because I wasn't able to do this prep, I would take all my time by getting it on the screen. But we had somebody sitting there, because you had to have somebody tending the terminal. They would get jammed, at least those older ones, the ones who'd been through their usable lifetime. And we'd say, we'd like to use our electronic bulletin board. We're using a computer. Pay no attention to the screen, later just came in. And I thought originally that about half the people walking in would say, a computer? Here? Oh no. Only one person ever did that. All the rest said, oh, a computer. Can I use it? Which of course you could. There were two holes in the box. Put your hands right in here and start typing. And if they didn't do anything and typed a return, it would give you a prompt on the paper about, well, here, think of a word and then type it in and then push the green button, which was the return. Okay, that worked much better than we thought it would. And the Rogers, at least, was designed for free-form keywording. It could take any word or set of words you wanted as index words and handle all the bookkeeping. That's the trick part of it. Fine, we got a going proposition. People were coming in, people were using it. The Computer History Museum has printouts from those years, and they're a little bit dim, but you can read them. It gets very interesting. Now, what were you using for a modem? The answer is not much. One of those varnished wooden boxes and so forth. And we had ideas that we wanted to run with CRT terminals at 300 baud. I mean, the modems at the computer end were limited to 300 baud. And we thought that if we're doing that, we might want to have a teaser screen that plays off of a cassette. When you think about it now, it really didn't make much sense because the line is still held open, and you're not wasting any resources, whether if you're sending versus not. But it seemed like a good idea at the time. And so I set out basically to design a modem that would do that. The modems we could get were all priced in the $300 to $350 region, new. And they wouldn't run off tape because cassette tape has a lot of wow, speed variation, which means the frequencies vary, sorry. And the whole trick with a modem is you've got these two frequencies 200 hertz apart. You're going 1, 0, 1, 0, etc. You got to discriminate between the two, and you got to set a dividing line somewhere saying, okay, this is the difference between 1 and 0. And if those are sliding around in the frequency spectrum, you got a big problem. Now, I had spent 4 years at Ampex before I got my degree. I was doing what I call my graduate work, working as an engineer there, and I knew that tape recording was a bad scene in terms of stability. Okay. So I had the benefit of talking with a number of pretty well-cooked minds at the potlucks that were held at the Community Computer Center in Menlo Park, 1919 Menalto Avenue, where they had a walk-in time-sharing computer system for kids playing games mostly. It was kind of a physical manifestation of Bob Albrecht's My Computer Likes Me When I Speak Basic, the kind of books he wrote for kids. So they were holding these potlucks on Wednesday nights, and a lot of people from the labs would come down there to talk about weird stuff like personal computers that didn't yet exist. And so I learned enough from them that it wasn't all that hard to do a modem, but the but part was the stuff they didn't talk about. There's something I call one of many MIT afflictions, which is the tendency to say, essentially all you have to do is da-da-da-da-da-da-da-da. And then they walk away having bestowed their great wisdom upon you, and it is your job to encounter all the problems and deal with them. Yeah, you can tell I didn't attend MIT. And so out of a certain amount of ignorance, I began, and this would have been well, we had already started the terminal in August, so it was the fall of '73, which is a pretty momentous year, because the TV typewriter came out then. That has nothing to do with this talk. And I count it as the beginning of the opening shots of the computer revolution. So there I was designing this modem. Now, fortunately, I had the benefit of a good education in terms of analog. Now, Otto J.N. Smith, I want to honor his name here. He was one of the, before I start telling this story, let me check the time to make sure I've got time for it. Well, sort of. Anyway, 1950, thereabouts, 48 and 50, there was the new four-engine airliners, DC-4 and DC-6. And they had a little problem, did I do that? Had a little problem with the wings falling off. And nobody knew why. They eventually tracked it down to an oscillatory phenomenon. It would go and get into a mode as the metal work hardened and so forth, where oscillations would tend to magnify, and that would, that can come to no good end, quite literally. At North American Aviation, Smith was a young engineer working on that problem. And one thing they developed was something called root locus analysis, in which it was a graphic design process you wrote the S plane. You had J omega. Stay in your place. J omega axis is the vertical one. Real axis is the horizontal one. Any complex number is real plus J omega imaginary, and that's a point on the plane. Now you're seeing this plane reversed, so I'm going to say the left half plane is the stable plane because the sigma, the real axis, real number, is negative, and that means any oscillation will damp down. If you go into the right half plane, it becomes positive. It is the exponent of e to the minus, or e to the j omega, or the e to the complex number. That goes positive, and so it comes up. So the plane, the poles, which are the actual solutions of the differential equation, for those planes was moving over, and they moved into the right half plane, and that's all she wrote. So they worked out this method of graphical solution, and more important, graphical expression, and they developed something called a SPI rule, which is a protractor and a ruler jammed together. He required us, when he taught the course that I studied on automatic control, required everybody to buy one. I don't think I ever used it. But he became a professor at UC Berkeley, and that's the one I studied under. And I came out of that experience with this graphic tool in my head, and I like to design with images. And so I was somehow able to invent an active filter. It sounds strange because active filters are really hard things to handle, as I understand, mathematically and so forth. I mean, but I just figured, okay, we have the S-plane here. We know we want to put two poles with a negative offset from the imaginary axis and be able to control where they go. And that means, and this is why it's a root locus problem. They will follow a locus, and this is the way, what we learned is you put a pole at 0 and a pole out here in the real land, and then you start increasing the feedback gain of the system. And they move together, and they break away, and they go high and low. And that's what I designed. I took an op amp. I think we got that on the screen, if we can make this screen light up again. Let me try to find some of these. Can't do it that way. Oh, here we go, window. There. Oh, there we are now. Here is the filter that I designed. And can you see it out there in the lower left corner? This is great. Can I make this large? I don't think I want to risk that. Anyway, there's a capacitor feeding back, and that gives it the pole at 0. That's the integrator. And then there's this network with two resistors and a capacitor in the center going to ground. That is a real pole on the 0 imaginary axis. Interestingly, they're feeding current back to the negative input, which is at 0 volts because the positive input is grounded, and the op amp will arrange that no matter what it has to do. So the two elements of the network are isolated from each other. They're just feeding ground as far as they're concerned. And if you didn't do that, if you used a Sallen key or something, they would interact, and oh my God, you've got problems. But anyway, this turns out to be a very easy filter to design and a very nice, stable one. And it even has something that makes it more stable and sharpens up the response. So anyway, you can basically Position these wherever you want. You can get the desired sharpness, which is a matter of, your test point moves up the j omega axis, and the distance from there to the pole is the denominator of the response. And it gets smaller and smaller and then bigger and bigger. And so that's a peaked response. So I pulled this off even before figuring out the right way to analyze it. I made a guess, and the guess paid off. So I've already used my luck. And, okay, I came up with a filter. Great. Now, how are you going to discriminate frequencies? The answer is phase-locked loop. And let's see if I can get that. Let's go. Oh, dear. Well, okay, now this I can rove around in this. Oh, this is good. This is the original. And we have the phase-locked loop. Well, it's a nice little square box. But what a phase-locked loop does, it's basically a voltage-controlled oscillator. And it usually produces a square wave. But it also does it by means of a triangle wave, which really isn't too relevant in this case. We'll get to this later when we come to the oscillator on the modem. And it's got a phase detector. And what is that? Well, phase is the degree along the cycle of whatever it is that's cyclical that you've traveled. So if some event happens 90 degrees at the 90-degree point, that's detected by the phase detector. Anyway, the simplest phase detector is an exclusive OR gate. But you have to clip and seriously amplify the inputs. But think of it as an exclusive OR. And if a 90-degree pair of waves, call them square waves, okay, will have put through an exclusive OR, give you a double frequency. And the important thing about that is that the high and low phases of that phase-detected wave are equal. The average is 0. So when it comes to, when you get to 0, magic things happen. You take that phase-detected wave, the exclusive ORed wave, and you put it through a filter, just an RC filter, and you get a voltage out of it, which, when you have the 90-degree relationship, is 0. And when the phase relationship moves out, it moves up, moves the other way, it moves down. That gets fed back to the voltage-controlled oscillator. Remember, it's voltage-controlled. And so that you set it up just right, and it will stabilize. They'll track the frequency of the oscillator with the input that's coming into the other side of the phase detector. Okay. So the 565 was the chip I had available. There's another one, 4046 in the CMOS area, and I prefer that one now, having had to break my eye teeth on this one. Well, okay, they have little application notes saying, here's how you make a modem out of this. And there's always this reference voltage. And it's always more or less a fixed voltage. Now, sometimes it's the integral of everything, but that takes time to stabilize. And here I am wanting to run stuff off of a cassette, which means it's going to be, you have the two frequencies, but they're going higher and lower all the time, more or less unpredictably. So what I did, can I get this thing back? I doubt it. I'm not sure there's a point to my trying to get it back. But we've got that PNP transistor. The A2 is just a differential amplifier and a filter. So I said you had a filter on the output. That's it. And you see this 22 microfarad capacitor, big honking capacitor there. and a little 1K resistor that can pull down on that capacitor and discharge it, and some larger 330K plus 10K resistors up there to charge the capacitor. It's charging from plus 12 volts. All right, so that capacitor will charge up until it reaches the voltage that's on the base plus 0.7 of a volt, plus the offset. Think of it as just the base voltage. So that when the base voltage comes down, the PNP transistor will conduct and discharge the capacitor to that level. It's an emitter follower. That's all it is. But it's going to find the negative peak of the voltage out of that op amp. And that peak voltage will start oozing up through the 330K resistor until the next negative going signal when it gets swatted back down. So I like to think of it that way visually. It's like bang, ooh, bang, bang. Why is this? Because of the marking stop bit. Every character ends with a stop bit. As I say, the stop bit can go on forever. That's the reference voltage. So now you start doing data and the stuff starts climbing up, oozing up, and all the negative peaks swat it back down again. And if the worst case your data is all zeros, then stop bit will do it. And so we got this 10K and 330K up there. You don't see off to the right. That's the reference voltage. It's offset by that a little bit. And so you think of the two frequencies, and they translate to voltages. And what you want to have the reference run in the middle, but be referenced to the negative, or either one of them, for that matter. And it worked. The thing self-adjusts its reference, and this was unknown with modems at that point. Everyone had, little cookbook, there I go again, cookbook Allen key filters. You didn't understand how they worked, but you filled in the values from the cookbook. What's my time coming to be? Yeah, we're okay. And then you had some frequency discriminator of some kind. And then you had a potentiometer, a multi-turn pot, adjust for the threshold. Well, we didn't. Now we have an automatically adjusting, continuously adjusting pot. So it did eliminate that adjustment, which meant that the modem could be sold as a kit. And the only real adjustments on it are the transmit frequencies. So now I doubt that I can get that page up, but we used a 555, which is your crude, simple charging RC timer. But we didn't quite use it the way everyone else uses it. We didn't, for instance, have an RC circuit with a resistor pulling up a capacitor so it would ooze up on an exponential curve. What I did is I built a current source, which is really, call it an emitter follower, one NPN going down and one PNP coming up. Actually, the current feeds out this way and is swallowed by the other one. There's a resistor in the emitter circuit, and so the voltage you apply to the base will have a relationship to that resistor, and that defines the current going through it. And this is a very workable current source circuit. It is temperature sensitive, so you have to compensate what that voltage on the base is with another junction at the same temperature. But you can build it pretty simply. So what I did was an I2I, charge with one current, discharge with twice the current, but don't turn the charging current off. So you turn that discharge on and off depending upon the data. This one stays where it is. Now, this one gets adjusted, and the pull down, the 2I, gets adjusted also. So there's two pots for that. And there's another 2 pots if you want to switch around the sex of the modem and have it be the transmitter, which you do if you're going to make a cassette. You have to do that. And so we have on the capacitor, it will charge up linearly with the 1I, and then when you pull 2I off of it in addition to the 1, the difference is 1I going down. You have a triangle wave. And that's what we feed out through an op-amp to the speaker. So instead of a sine wave, it's a triangle, which is a pretty close approximation. And the damn thing seemed to work. I got it working in late '73. We tried it out on the terminal, worked like a charm. We tried it out on a CRT terminal, worked great at 300 baud. The thing with those filters was able to, it could handle like minus 50 dBm, which is a very small signal, coming off of a wired source. And then when I used a loudspeaker as a microphone, which you can do, listening to the phone line, it had to be greater than 35, greater than 35 or negative 35 dBm, which means I went out and bought a poster of a train wreck on a bridge and somebody standing there saying, "Oh shit," which is how I felt about that. But that's what we ran with. So for acoustically coupled operations, it was minus 35 dB online, which isn't too bad. But it ain't 50 dB. 50 dB is something to boast about. So there I was. I'd built one of them by hand. Now we fast forward to 1975. Fourth meeting, I don't know if it's the fourth meeting, but around there, after the Homebrew Computer Club. One of the originals is Martin J. Spergel. And he had been, as a little business, selling bags of parts for construction articles in Popular Electronics and other magazines. So he had a little business going, M&R Enterprises. R is Rona, his wife, Marty and Rona. And he attended the first meeting. He gave away an 8008 at that point, which really gained him cred. And sometime at or after the fourth meeting, he approached me and says, "Why don't you give me a design of a computer to build?" Well, you know, it's not that easy, right? I said, well, okay, that would take a while, but I happen to have this modem. And that's when he probably first heard the word modem. He took it and ran with it. We signed a royalty contract. I got $10 a unit. And he, in fact, brought in other people from the club to finish up the design. I did the layout of the circuit board. They did the manual. I helped with all that. It all worked. And I don't recall when they first shipped, but it would have been, well, they put it in the July '76, I believe. No, that's not true. Popular Electronics, I think it was January, I'm not sure. He managed to have one case made with a heat-formed, smoked plexiglass cover. Sexy as hell. And that's what they put on the cover. And that was the only one that was ever built. So he got a lot of attention out of that. He very carefully did not have the actual details of construction, and the circuit board was shown, but it was at a non-standard size. One or two people contacted me and said, you know, what can I do to make this work? Well, I don't know. I hope they got given modems. But he shipped it, and it was a success. It was priced initially at something like $97, but that went up to about $109, which is pretty good in a market where the units are selling for $350. And that knocked prices down. And he had a good run with that. I had a good run with that. They didn't bother me much. They fielded all the service calls, and they would, if you needed really to adjust your transmitting pots and couldn't do it yourself, send it in, we'll do it for you. So I greatly appreciate that. He showed a lot of class in that, and he got M&R up and running. So that's, now another point, I never tested it with cassettes. Shame, shame. I don't really know anybody who did, but somebody must have. And if they want to talk to me about it, here I am. I was invited to participate in the Kansas City Tape Standard meeting in January of '76, I believe, in Kansas City. And MITS was there, you know, the Altair people. And their idea of a tape standard was a 103 modem with no floating reference, which was just waiting for the cassette machines to blow it out of the water. Well, what we came up with was the Kansas City Standard, which is Don Lancaster's synchronous standard that derives the UART clock as a 16 times data frequency from the data itself. Now, that was limited to 300 baud, and never, you know, it was implemented in various places. But I brought the Pennywhistle there and said, well, I've got a 103 modem with compensation for frequency shift. Well, neither of those made it, but I was happy to do that there. Okay, if anybody has any questions, maybe now's the time, because I think we have about 7 minutes, according to my clock. Yes, young man. You don't know how old I am. Yeah. Was that made for storage? Yes, that was it. At that time, was any of these devices available for storing the data that was coming in on modem? Nobody was doing it that I know of, for the very reason I had to create this floating reference. You can't really predict your tape speed or keep it in one place with a cassette recorder. It's just too cheap. Well, it should have worked. Put it that way. Any more questions? Yes? Well, I'm glad you asked, because I forgot to tell that. I was born and raised in Philadelphia, and we all learned about Benjamin Franklin and how, in his youth, he once spent a penny or something on a penny whistle and was ragged about it by his parents and all his friends or whatever. And so that instilled in him his habits of frugality. You know, a penny saved is a penny earned, not spent on a damn penny whistle. Now, when it came time to name the modem, the first thing I came up with was an amateur radio term, peanut whistle, which is a term for a tiny station less than 5 watts or something. And you can build those, a nice, you know, design problem and construction problem. And I figured, okay, call it the peanut whistle. Now that's two things. Peanut can in some quarters be seen as a slightly rude word, or a rude first syllable. And also, this isn't an amateur radio thing. So I didn't want the amateur radio guys to think, oh, it's one of ours. It'll work with us, won't it? Well, it's not made for those frequencies. So I thought it's going to be cheap. Call it the penny whistle. And I put the 103 on there because that was the bell standard that it would meet, and thus the name. So it is homage to Benjamin Franklin and kind of negative homage to amateur radio guys. I guess that's it. In a certain sense, in a nice way. Anything else? Okay. Oh, so odd, interesting facts that I may have failed to lay out at your feet. Marty made the product possible as a product because he located a warehouse full of Reykjavik modem cups, the things you put the phone into. I wouldn't have had a clue where to find that, but he was the junk man, and he could do that. And so once that happened, and I realized that, see, I had already gotten one of the donated modems that Resource One had, something it was called, I think by its people, the Meatloaf. I don't remember the name of the company, but it was a drawn aluminum case, very plain. It had two little small tin cans in it. And we were lined with urethane foam, soft urethane foam. And they had a little speaker tucked in the bottom with more foam. So basically the phone went into the tin cans and it came up close to the speaker, and this apparently worked. So I figured I could do that. And so the Pennywhistle had two little speakers, one functioning as an output and one functioning as an input. They work as dynamic microphones because it's moving a coil within a magnetic field as a microphone. And this is why you have intercoms where you don't have to have a separate mic. If you look inside, you might find that you just throw a switch and the speaker turns into a microphone. That is the old vacuum tube way of doing it. Nowadays, little tiny electret microphones are so cheap that maybe don't do that. So that's what I was using. And Marty found the way where to get a warehouse full of these things. Marty Spergel went on to a great future, basically selling the Super Mod. And in fact, they included a little advertisement for it in the box because, here's what I need to tell you. I received from an anonymous source an unbuilt Pennywhistle modem kit. I opened the box, which you're not supposed to do. I had to check to see if it was what it said it was, and it was. It was a real thing. I closed up the box. I wrote Pennywhistle Modem on it, so that's there. And now, just recently, I was contacted by RR Auctioneers. They, I think, have a booth on the floor. And we'll be talking here on tomorrow. So I am putting that up for auction with them. Now, not all at once, unless you have something in the 5 to 6 digit region worth of money. I'm going to try to flog that for all it's worth. And this is kind of part of that, I'm ashamed to admit. Yes? They're going to auction it for me. Auction. How much do you want to pay? Well, they say 300, but that's ridiculous. I'm going to set a bottom price. It's more like, say, $300. I'm going to set a bottom price of like, $1,500 or $5,000, something of that sort. But if you have to settle for that price, you lose. I don't want to lose. Do you know of another? Do you know where you'd find another? Well, I'm not saying they all got built is the point. This is unbuilt. It's a kit. According to my best recollection of the royalties, it would be somewhere around 850 or something. My best guess. But I could well be off by 25 to 50%. So yeah, it's spread the word among all your too rich friends. That comes later. I thought I had 3, but I have 2. And what I want to do is make them presentation grade and crank that for all it's worth. It's like, this is the ultimate bar mitzvah present. Don't touch it. The wood's all been polished, but there it is. None of the solves I have work because I believe the bits in the EEPROM have degraded to some extent, which you solve by reprogramming them. But I tried everything else. So in one case, all the chips are soldered in. That didn't work. And then on solves, you have to refurb the keyboards. But that's another matter. That's another talk. Maybe tomorrow we can talk about that. I think I'm out of time. Goodness, I'm 1 minute over. Will I ever be forgiven? Sorry about the lack of real slides. And what I'm going to do is to put that together and put it up on my Patreon page. You basically don't have to pay them anything to read that. But if you want to get the each month's essay and so forth a little ahead of time, that's what paying is for. Plus, if you want to give me some money, which is a nice thing, that's how you can do it. But I'm going to publish it there out of contrition, and also because it's good advertising. That's it. And thank you. What? Another question?
Are you willing to sign stuff?
Why not?
I set up a table for you.
Oh. Okay. Now you're taking me back to Rome in 2018, where I was the attraction, although they did pay me and so flew me over there, and I never paid for anything. But man, I signed everybody's card, which was fun. I'll be at the table. This is Bob Alker, and he's a shill. So far, but the future is still ahead of us.